Okay, welcome back to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 1.2, day 2, entitled Exponents and Radicals. And today we're going to talk about the bottom three objectives. We're going to talk about radicals, which are square roots, cubed roots, fourth roots, etc. We're going to talk about rational exponents, and those are exponents that can be written as a ratio or a fraction. And then we're going to refresh your memory on rationalizing the denominator, which is always a favorite concept from Algebra 2. So let's kick things off with radicals. And we know what 2 to the n means whenever n is an integer. It means 2 to some power. So to give meaning to a power, such as 2 to the 4/5, whose exponent is a rational number or a fraction, we have to discuss radicals. So here's our symbol for our radicals, and that means the positive square root of something. And when it's a square root, we technically don't put the little 2 in there. Technically, there's a little 2 there in that little elbow. You see that when it's a cubed root or fourth root, etc. So what that means is that the square root of a is b, and if that's true, then b squared is a. Okay, so that would be like the square root of 25 is 5, and 5 squared is 25. And that's kind of what they illustrate at the bottom here. The square root of 9 is 3, and 3 squared is 9. And we have a definition for the nth root of something. So that is just that same expression we were reviewing on the previous page, just written out with variables. So the nth root of a is b, and that means that b to the n power is a. And there are lots of properties of square roots. When we have a big product inside a radical, though, we can break that down into two smaller radicals that are being multiplied together. And that we're going to do in a little bit in example 9. We'll take big numbers like the square root of 50 and break the 50 down into 25 and 2, because we can take the square root of 25. Okay. Same thing for the second property here. You can take a fraction and you can break it apart and make the numerator a radical and the denominator a radical. When you have a root of a root, the shortcut is to multiply the roots together. It's kind of like when you have a power to a power, you multiply them together. And then we have some other properties here, 4 and 5, and these I'll elaborate on a little bit more in our example 8 coming up. Anytime you go from an even power to an odd power, you have to put absolute value bars around your answer. And I think that's best illustrated in an example. So, for example 8, we have this huge, complicated, scary-looking radical. We have the fourth root of 625, p to the 8th, and q to the 4th. It's not really as scary as it looks. We're going to break it down into its 3 parts. We've got a number part, and we've got a p part, and we have a q part. And basically all of these are being taken, or the fourth root is being taken of all of these. So I have the fourth root of 625. And that's actually a perfect fourth. I can take the fourth root of that. You can do that on your calculator, and you get 5. See, that's not so bad. And we can take the fourth root of p to the 8th. When you take a fourth root of an exponent, you basically are dividing the exponent by the root that you're taking. So 8 divided by 4 is 2. So you get p squared. And then we also have the fourth root of q to the 4th. So again, we're going to take that exponent 4, and we're going to divide it by the power, or I'm sorry, the root that we're taking, which is 4. So 4 divided by 4 is 1. Now, we have one last little itty-bitty step. And this is the step on the previous slide that I said I would illustrate in an example. When you go in your original problem from an even power to an odd power in your answer, you have to put absolute value bars around that term. So in the original problem, p had a power of 8, or an exponent of 8, which is even. And in our answer, p is now squared. 2 is also even. So that's good. We went from even to even exponent to even exponent. But the q in the original problem was a q to the fourth. Now in my answer, it's a q to the first. So we went from an even exponent to an odd exponent. So that is where I have to put absolute value bars around just the q, because we want to make sure that q stays positive. Because if we raise it to, if we have a positive number that we raise to a fourth power, we get a positive answer. And if we have a negative value for q, when we raise it to a fourth power, we will also want to get a positive answer. So even though we've simplified it in our answer now to the first power, we still want to make sure that that value stays positive. So that's why we need those absolute value bars around just the q. So it's annoying, I know, but it's just an extra little step that you got to do before you walk away from a problem. Make sure you didn't go from an even power or an even exponent in the original problem to an odd exponent in the answer. If you do, just put absolute value bars around it and you'll be good to go. Now part B is a little bit different because we can't divide 4 by 3. 3 doesn't go into 4 evenly. So what we do then is we break down this x to the fourth, because it's really 4 x's. And if I can have a certain amount of those x's, I could cancel out this cubed root here. And the way that I kind of cancel out that cubed root, even if it's just a little bit, is to kind of divide it out. So I have to find an exponent that I can divide by 3. Well, if I made this x to the third and x to the first, if I multiply my bases together, I have to add my exponents together. So 3 plus 1 is 4. So I really haven't changed how many x's I have. I'm just breaking it into 2 little separate pieces instead of one big chunk of x to the fourth. And now, if I take the cubed root of each of these, you should notice that I'll be able to take the cubed root of x to the third. And that 3 in the exponent and that 3 in my root will cancel out. So that'll get me x to the first, or just x. Now I'll still have this cubed root of x, or x to the first, left over. That term I can't simplify. I can't divide 1 by 3, so he's just going to be my little leftovers. So that's all I can do for that problem, is break it down so that I can take out as many x to the thirds as I can, since I have a third root. Now example 9, this should be pretty similar, especially part A. This you should be familiar with, and part B is going to be similar to what we just did. But part A, you should have done this in algebra and geometry, so you should know that we're going to take these big non-perfect square roots and we're going to break them down into perfect square roots. So 125, I have to think, okay, what's the biggest perfect square that'll go into 125? Well, that's going to be 25 times 5. 25 is a perfect square, and it goes into 125 5 times. Now, I can't take the square root of 5, but I can take the square root of 25. So that's 5 square root 5. So I can't simplify that problem all the way, but I can simplify it more than it was. And then I'm going to do the same thing with 245. I'm going to think, okay, what's the biggest perfect square that goes into 245? And you might have to remember what your perfect squares are. 4, 9, 16, 25, etc. And you might have to sit there and divide on your calculator. Try 245 divided by 9. Try 245 divided by 36. And you should eventually realize that 49 and 5. If you multiply 49 times 5, you get 245. And 49 is the biggest perfect square that goes into 245. I know that because this 5 can't be broken down anymore. And it's also the same as this other radical over here. So now I have 7 square root 5, because the square root of 49 is 7. I am adding these two terms together. And the only way we can add radicals together is if they have the same radical. So I can't just take 125 and add it to 245 and make it one big square root. I can do that for multiplication, but not for addition. For addition, I have to break them down and get them to have the same radical. So I have the square root of 5 and the square root of 5. So now it's kind of like they're like radicals. They're like terms. So I can add the numbers out front. The 5 and the 7 gets me 12 square root 5. Now for part B, we do want to assume that B is greater than 0, so we're dealing with positive numbers here. And I have the square root of 25b minus the square root of b to the third. Now you want to see both terms within this square root. We've got a 25 and we've got a b. Now I can take the square root of 25. That's no problem. But that b, I can't take the square root of him. That's b to the first power. I can't divide 1 by 2. If it was b squared, or b to the fourth, or b to the sixth, or b to any even power, I could divide that out and take the square root. But b to the first, 1 is an odd number. I can't divide it evenly by 2. So I'm just going to break this down into 5 and the square root of b. Now this b to the third, this is very similar to what we saw in the previous example, example number 8, part B. Here I have b to the third, and I'm trying to take the square root of it. So the square root is a 2. There's a little invisible 2 there. So I want to ask myself, okay, how many of those b to the 2's can I take out of this b to the third? I'm going to break it down. I'm going to break it down into b squared and b to the first. 2 plus 1 is 3. And now if I take the square root of b squared, I can actually do that. Okay? So the square root of b squared is going to be b to the first. And then I'll have that square root of b left over. And I am subtracting these two terms. That was in my original problem there. Now, you can leave your answer like that if you would like to. That's totally fine. Your book is going to simplify it just a little bit. Okay? Now, they are like terms. They have the same radical, but I can't subtract 5 and b. So your book is going to write it 5 minus b times the square root of b. That's how your book's going to write it. Now, if you want to leave it like we had it, if you want to leave it like this, that's totally fine. That's totally acceptable. Okay, now we're going to talk about rational exponents, or fractional exponents. That's what rational means. And this can be a little scary. To define what is meant by a rational exponent, a fractional exponent, such as 1/3, we need to use radicals. Okay, so there's a connection between taking a square root and a fractional exponent. So we have this a to the 1/n power. And basically that's like taking a to some root. So I think if we look down here at the very, very bottom of the screen, that makes the most sense. And it makes the most sense if you kind of read it backwards. If we had a that we were taking some power of, like a, or I'm sorry, some root of, if we were taking the third root of a to the first power, we can rewrite that as a to the 1/3 power. And you should have seen this last year in Algebra 2, so this shouldn't be a completely new concept. And this expression, we can rewrite it from left to right, or we can rewrite it from right to left. They're interchangeable. We can go back and forth between them. Sometimes it's easier to work with fractional exponents than it is to work with radicals. Some people prefer radicals over fractional exponents, but you need to be familiar with both. And that's basically what this little box explains here. If you have a to the m over n power, that is basically the nth root of a to the m. So whatever is in the denominator of that fraction becomes the root that you're taking. And that m in the numerator becomes the power on the a. They have it written kind of funny there. I guess it could be written anyway, but usually it's the nth root of a to the m power. You want to keep that inside, like over here. That's a better way to think of it. So let's try this. Let's see if we can simplify these expressions. Now they're given to us as roots or as radicals, but we're going to try and work with them in a fractional form. Okay? So this cubed root of a, that is really a to the 1/3 power. And then the second part here, the cubed root of a to the 7th, that would be a to the 7/3 power. So again, the root you're taking becomes the denominator. And now we're multiplying our bases together. So we need to add our exponents. So this is going to be a to the 8/3 power. Now technically you could leave your answer like that. That's correct. However, the problem was given to us as a radical, so we want to write our answer as a radical. So here's how we do that. We got to kind of break down the 8/3. Okay? 8/3 is an improper fraction, and if you rewrote it as a mixed number, it would be 2 and 2/3. So what that does for our radical is that it means we have two whole a's that we took out. So we have an a times an a. That's that whole 2 out front here. So we have a to the 2nd power. And then this 2/3 is kind of like our little leftovers. We still have a cubed root because our denominator is 3. And we have 2 a's inside here that we're taking the cubed root of because we have this 2/3 left over. 2 is the numerator in that 2/3. So the more appropriate way to write the answer is this way. Since our problem was given to us as a radical, we want to write it as a radical. But I think this is more simplified. That makes a little bit more sense. Okay, so either form is technically correct. They're equivalent. Now the nice thing about part B is that it might look a little scary, but actually it's given to us with fractional exponents, so we can leave our answer as a fractional exponent. So all we're really doing here is we're applying the properties of exponents. In my numerator, I'm multiplying the bases, so I'm going to add my exponents. So that'll give me a to the 9/5. And then my denominator is just a to the 3/5. So now that I have one numerator and one denominator, now I can use the rule where I subtract my exponents. So 9/5 minus 3/5 gets me a to the 6/5. And I can leave my answer like that since it was given to me in a fractional exponent form. If I wanted to rewrite it, I could. I can rewrite it as a radical. And again, we want to think of 6/5 as an improper fraction. So that would really be 1 and 1/5. So that means I would have one whole a that I would pull out, or a to the 1st power. And then I would have the 5th root of a to the 1st left over. So the 1, the whole 1, is right here that I pulled out. That's that a to the 1st. And then my fraction, my fractional part, that becomes my radical. Now in part C and part D here, we're still going to use these properties of fractional exponents. And in part C, I have 2 times a to the 3rd and b to the 4th, but it's all being raised to a power of 3/2. Now, if that was being raised to just the 3rd power, we would distribute the 3 to every single term inside the parentheses. We're going to do the exact same thing with the 3/2. I'm going to give everything a 3/2 power. So even though it's a fraction, we're still following those rules for exponents that we talked about yesterday. So now I'll have 2 to the 3/2 power, and I'll have a to the 9/2. You're multiplying 3/2 by 3. You're multiplying them together. And then I'll have b to the 12/2, which is also b to the 6th. Okay. Now I can simplify this a little bit more. I can break things down just to simplify them. This 2 to the 3 halves. Okay, again, 3 halves is kind of like 1 1/2. I'll write that over to the side so we don't get confused with the rest of the fractions in the problem. So that means I have a whole 2 that I'm pulling out, and then I have a 2 to the 1/2 power that's kind of left over. So that's a square root of 2. Okay? 2 to the 1/2 power would be 2, the square root of 2. And then I have my a to the 9 halves. I can't really do much to that, but the b to the 6th. I can divide 12 by 2 and get 6. So your book would write the problem this way. 2 and the square root of 2, and then a to the 9 halves and b to the 6th. Now if you wanted to break it down some more, you could. You could take that 9 halves and you could think of, okay, 9 halves would really be 4 1/2. So then this would be a to the 4th, and then you'd have a square root of a left over as well. So if you wanted to break that down one step further, you could. Now you've got 2 square roots. You have a square root of 2 and a square root of a. So to simplify it as much as we can, we want to combine all of our non-square root parts of the term and our square root parts of the term together. So this is a lot of little itty-bitty steps. But technically, if you left your answer like we had it up here, you probably want to do the 12 divided by 2 is 6, but you could leave everything with a fractional exponent. You could break down the number. Ultimately, you want to break down the number and any variables as well, so that you have as many whole numbers and whole exponents as you can possibly have. And for part D, whew, that one looks like a beast. The nice thing is we've got a 3 out front of this first set of parentheses. So we have a nice whole number that we get to distribute this time. So I am going to distribute it to every single part of the term inside the parentheses. And the nice thing is when we do that, we get 2 to the 3rd, and then we get x to the 9/4. And then in my denominator here, I get rid of that 1/3. 1/3 times 3 is just 1, so I just get y. So that's nice. Now in my second term, I don't really have anything that I have to distribute, but I do have a negative exponent, and that's bad. So we want to try and get rid of that. We want to move that negative exponent from the denominator up to the numerator, so it'll be positive. So that's what I'm going to do here. I'm going to leave the y to the 4th, but then I'm going to leave x to the 1/2 in the numerator. So it'll be positive instead of leaving it negative 1/2 in the denominator. So now I can multiply across my numerator, kind of combine my terms here. I can do the 2 to the 3rd. That's going to be 8. Let's see, x, I have 9/4 and 1/2. So I have to add 9/4 and 1/2. 1/2 is really 2/4. So it's like 9/4 and 2/4. So that's going to be 11/4. So I'll have x to the 11/4. And now my y's, I have y to the 4th here in the numerator, and the only thing I have in the denominator is another y. So I can leave the y to the 4th and my y here in the denominator, but I'm going to have to cancel those. I'm going to have to cancel the 1y out from the denominator. So this will be 8x to the 11/4 y to the 3rd. And to cancel that y from the denominator, we're using the subtraction property of exponents. If I have 4 on the numerator and 1 in the denominator, it's kind of like canceling off the 1 and subtracting a 1 from the 4 to get a 3. Okay? Again, you can leave your answer like that. That's totally fine. If you want to break down the 11/4, think of 11/4 as 2 and 3/4. 4 goes into 11 2 times, so that's 8. And then you have 3 more to get to the 11. So that would be still an 8, but you would have 2 whole x's that you would pull out. And then you would have, kind of running out of room here, you would have your fourth root of x to the third as your leftover. And then you would have your y to the third. And really we would want to rewrite that like we did for part C, where all of our terms are together. So let me write it off to the bottom here. We want all of our whole terms, like the 8 and the x squared and the y to the third. We want all of those whole terms together. And then any leftovers can go together at the end. So any leftover radicals. Okay. So you can leave your answer with the fractional exponent or break it down even further and have as many whole number exponents as you can have. Okay, last concept. Not nearly as tough as it sounds. I think the examples we just went through were a lot more detail-oriented, a lot more time-consuming. Rationalizing the denominator just basically is a concept that says you can't have radicals in your denominator. Your calculator can handle them now, but they couldn't in the past. So this was a process that mathematicians had to go through just so they could do calculations on their calculator. But basically it's not allowed in the denominator. The denominator is a very exclusive club. It doesn't want any radicals, doesn't want any negative exponents. It just likes nice whole numbers or whole exponents. So to get rid of whatever radical is in the denominator, you basically multiply the top and the bottom by whatever you need to make a whole perfect root. So if you're dealing with a square root, you can multiply it by itself. Any square root that you multiply by itself, the square roots are going to cancel. But we're going to see some examples in a moment where we might have to multiply by some part of a root, some fraction of a root. We might have the fourth root of a to the third. So we don't need another fourth root. We just need one more a. So if we have a to the third, we need a to the first. If you added those exponents together, you'd get a to the fourth, and then you have a perfect fourth root. So it's a lot of mental math with fractions in this chapter. So for part A here, to simplify this, to rationalize this denominator, we just got to get rid of that square root. So all we have to do is multiply numerator and denominator by that square root. So now we'll have 2 times the square root of 3 over 3. Square root of 3 times the square root of 3, that's the square root of 9. Square root of 9 is 3, and you're done. So ideally, you have square roots in your denominator, and you can just multiply by that square root and get it out of there. However, you're in pre-calc now. It's more advanced mathematics. So you got to think of example B and example C as higher level math. Okay? For part B, we can't just multiply by another 8th root of x to the 7th. Okay? We can't divide 7 by 8. It doesn't divide evenly. But I need a number that I could divide by 8 evenly. And 7 is pretty close. It's 1 away from 8. So I'm going to multiply by the 8th root of x to the first in the denominator and the numerator. Because if I have x to the 7th and x to the first, and I'm multiplying those bases, I can add my exponents. And when I add those exponents, I get the 8th root of x to the 8th. And I can divide 8 by 8, and I get a whole x. Bye-bye radical. Now my denominator is legal. And in my numerator, I just get the 8th root of x. It's being multiplied by 1, so I can just leave him. The numerator is very welcoming. It doesn't mind radicals. It doesn't mind fractional exponents. Okay? So we can have radicals in the numerator, just not in the denominator. Now for part C, very similar concept, except I have a big fraction now inside this radical. So my very first step is going to be to break this apart. I want the 7th root of 1 and the 7th root of a squared. Now the 7th root of 1 is just 1, so that really doesn't complicate things too much. But in my denominator, I can't have that 7th root. I got to get rid of them. Now, I need to not multiply by itself because it's not a square root. I need to multiply by some amount of a's, a to the something, that's going to add up to 7 so that I can divide 7 by 7. So I need to multiply by the 7th root of a to the 5th, because 5 plus 2 is 7, and I can take the 7th root of a to the 7th and get a nice whole number. If I do that to the denominator, I have to do that to the numerator as well. So now my denominator is really going to be the 7th root of a to the 7th, which is just a. And in my numerator, I have 1. The 7th root of 1 is just 1. And then I have the 7th root of a to the 5th. So we can part B, that's still just the 7th root of a to the 5th. I can leave it that way. Now if it helps, think of them as fractions. Think of those denominators as fractions. Think of this as a to the 2/7 and a to the 5/7. 2/7 plus 5/7 is 7/7. 7 over 7 is 1. Okay, so we have a whole a to the first power. We have one whole a. So we're trying to get rid of little pieces, little fractions. We want nice whole numbers for our exponents. So this homework is maybe going to be a little more detail-oriented, might take you a little bit longer. There are a lot of odd problems though, so you can check your answers in the back of your book. If you have questions, come on in before school and see me and I'll help you out.